بسم الله الرحمن الرحيم. تابع معكم من سلسلة محاضرات chapter 4. الآن رايحين نعرض chapter 4 section 5 non-constant coefficients reduction of order. إذا الطريقة الأولى اللي شفناها قبل non-constant coefficients كانت only applied for Euler-Cauchy equation. هلا رايحين نعرض طريقة تانية اسمها reduction of order، رايحة تحل كلاس أكبر من ال non-constant coefficients، لكن أكيد فيها محددات. راح نشوف هاي المحددات خلال هذه الرول. So I'm going to start with rule number 1. Actually we only have one rule. Let y1 be a given solution to the differential equation second order linear y double prime plus pxy prime plus qxy equals to 0 in an interval AB where p of x and q of x, the coefficients, are continuous on AB. Then y2 given by the formula y1 times the integral of exponential for the integral of minus p of x is the coefficient of y prime dx over y1 squared dx. So this y2 is a linearly independent solution of y1. Hence, the general solution is given by the formula c1 y1 plus c2 y2. Now let's go through the derivation for this rule. Actually, this rule is called the reduction of order rule. So the derivation for this rule, since we need a linearly independent solution, so the solution must be non-constant times function times y. So v is v of x. This is non-constant. So v of x is non-constant. إذا بهذه الطريقة إحنا متأكدين إنه ال y2 is not linearly dependent, is linearly independent لأنه هو multiple of a function, not multiple of a constant. So if we assume y2 is a solution for the equation above here and y1 is a solution, so what we have is y1 double prime plus p of x y1 prime plus q of x y1 equals to 0. So this is equation number 1. And also I have y2 double prime plus p of x y2 prime plus q of x y1 y2 prime per 2 equals to 0. So this is number 2. So we have two solutions satisfying the equation. So I have equation number 1, equation number 2. But again, y2 is the function y1 times the function v. From here we can find y2 prime by product rule, which is y1 times v prime plus y1 prime times v. And hence y2 double prime will be now product rule for both sides. So we have y1 prime times v prime plus y1 double prime times v. I'm here, no, now y1, so I have y1 times v double prime. Yes. Now plus again y1 prime prime, which is double prime, times v plus now y1 prime v prime. I have here like terms, so I can simplify y double prime to be y1 times v double prime plus y1 double prime times v plus 2y1 prime v prime. So here's y double prime. Now plug y2 and y2 prime, y2 double prime in equation number 2. So from equation number 2, what we get if we plug all of these, so I have y2 double prime, so it means now what we have, so y2 double prime plus p of x y2 prime plus q of x y2 equals to 0. So y2 double prime Now let's see, it is now y1 v double prime plus y1 double prime v plus 2 y1 prime v prime. So all of this is y2 prime. Now plus p of x times y1 prime. So y1 prime will be, now from here, is y1 v prime plus y1 prime v. So it is y1 prime v plus y1 v prime. Finally, plus q of x y2 equals to 0. So now we will use also equation number 1, which says that y1 is a solution. So all of this is 0. So let's factor out this term. I mean, we will now choose y1 double prime from here, y1 double prime. And also we have y1 prime times p of x, and we have y2. Actually, if I now, yes, if I now replace y2 by y1 times v, if I replace y2, because y2 is y1 times v, then also I'm going to take this term. So I'm taking the term y1 double prime and the coefficient of p of x y1 prime and the coefficient of q of x y1. Collect all of these terms. We have here now, we have y double prime with v, so I can factor out v, plus p of x y1 prime plus q of x y1 times v, plus now the rest becomes y1 double prime plus 2 y1 prime v prime plus p of x. Now here's the term p of x times y1 v prime equals to 0. So, but all of this term now is 0 because y1 is a solution, so this equals to 0. So now we reduce the equation to the following form. y1 double prime is a given function, 2y1 prime is a given function, times v prime plus p of x y. Here's I have y1 v double prime. I have to put it somewhere. So I now fix it. It is y1 v double prime, y1 v double prime, and again I have y1 v double prime plus 2y1 prime v prime p of x y1 v1 equals to 0. So the equation in terms of v double prime and v prime. So now here it's second order. How about if we set v prime to be u? So replace v prime by u. Now we convert the equation into first order differential equation. So this is u prime. Now here I have u prime equals v double prime. So plus 2y1 prime times u plus p of x y1 u equals to 0. So now we reduce the order from second order to the first order equation. So here's the idea why we call the method to be reduction of order. We reduce the order from second order into first order. Now we solve this equation. Actually, this is a separable equation. So let's solve this equation in terms of y. So what we have is u prime. So I can write now 2y1 prime plus p of x y1 times u equals minus y1 u prime. Now divide over u, both of sides, you get u prime over u, and also divide over minus y prime cancel out here. So divide over minus y1 prime, we get minus 2y1 prime over y1. I divided over y1 here. Now, minus p of x, cancel out y1 with y1. We get now u prime over u. Now we integrate both sides. So the integral of the first term is natural log of u. I can take out the absolute value because we can choose the constant to have plus minus for the absolute value. So we can write this equals to, now the integral of this term now, it becomes minus 2 natural log of y1 plus the integral of minus p of x. We don't know what is p of x. Now we pull up negative 2, so natural log of u, it equals to natural log of y 1 to the minus 2 plus integral p of x dx. Take exponential of both sides, we have u equals e to the y2 to the power negative 2. So I cancel the function with its inverse, so I only get y1 to the minus 2 plus becomes now product because e to the a plus b actuates e to the a, e to the b. Now I'm using this fact here, and this now becomes e to the integral of minus p of x dx. But remember that now u is v prime, so v is the integral of all this term here. So I have the integral of e to the minus p of x dx over y squared here, y1 squared dx. So here's v, the factor of y2. So again here, now we have y2 will be v times y1, and we are done. So here's the derivation for this method. So finally, we have to memorize this result. V, or let's say y2 is y1 times v, and here's the function v. But the problem with this rule, I have to have a one solution to find the other solution. So now let's see how to apply this now by example. Solve the differential equation xy double prime minus 2y prime equals to 0 for x greater than 0. So here now we just use the idea for the reduction of order. I will not use the rule for reduction of order because I have here y double prime and only y prime, so I can reduce the order from second order to the first order by setting. So set u to be y prime, then u prime will be y double prime, and I can convert the equation into first order y u prime minus 2u equals to 0. So I will separate x and u. Here's now the equation x u prime equals 2u. Now I divide over u because I have u prime over u is length. So divide both sides over u and divide both sides over x. So what I have here, xu, so you cancel out, and the equation now becomes u prime over u equals 2 times 1 over x. Integrate both sides, we get now natural log of u equals 2 natural log of x plus a constant, I'm going to call it k for example. Now pull up 2, so it becomes x squared. Take exponential for both sides, so u equals x squared times e to the power k. Of course I have here absolute value, now absolute value with plus minus, and I'm gonna call all of this by c. So u, it equals c times x squared. So remember that we have here absolute value. You don't have to write it actually because always I can drop it by taking a new constant. So now u is v prime, y prime, so I have y prime equals c times x squared. So integrate both sides, you get now y equals c x squared plus other constant, let's call it for example k. I'm sorry, c x cubed over 3. So now here also I can keep calling c over 3 by c, for example, no c. So here's, I can write this in this form. So here's the final answer. Remember, this c is different than this c. Let's take another example now. Given that y1 equals e to the t is a solution to the linear differential equation ty double prime plus t minus 1y prime plus y equals to 0, where t is greater than 0. So find the general solution. Now, to find the general solution, we know the first solution, and notice that we have non-constant coefficient, so we cannot use the characteristic or auxiliary equation to find the solution. Here's now, if I write this in standard form, I can find y2. So first of all, I'm going to write this as standard form. So the only thing that we need to divide over t squared, so I get 1 minus 1 over t times y prime plus 1 over t y equals to 0. So here's p of x actually. Here's a prime, and this is p of x or p of t. So the solution, the other linearly independent solution will be y1 times v. So let's compute v, and v by the formula will be the integral of exponential to minus p of t dt. I'm using t now, over y1 of t squared. So let's first of all find this term here. So we only need to find the integral of minus p of t dt. Now, which is actually the integral of 1 over t minus 1 dt, because I multiplied by negative here. So this integral now becomes natural log of t minus t. So here's the integral now, taking the exponential for this term. So e to the natural log of t minus t now becomes e to the ln of t times e to the minus t, so which is t e to the minus t. So I computed this term here. Now let's compute v. So v is now but the formula is the integral of what we have found here. It is t times, so it is t times e to the minus t over y1 squared, or y1, it is now y1, it is e to the t, so I multiply, divide over e to the t squared dt. This equals to t times e to the minus 3t, because I have e to the 2t and e to the minus t, so put up you get this integral. Now this integral can be done by parts, so I'm going to use the tabular method. So I have t, I have here e to the minus 3t, so if you divide, differentiate, you get 1 is 0. If you integrate, now you get e to the minus 3t times minus 1 over 3, integrate again, you get 1 over 9 e to the minus 3t. So multiply, alternate in sign, positive, negative. So the answer now will be minus t over 3 e to the minus 3t, now minus 1 over 9 e to the minus 3t. So here's v. Okay, So now y2 will be y1, which is e to the t, times v. So I have minus 3 over t minus 1 over 9, factor out e to the minus 3t. So y2 will be now minus t over 3 minus 1 over 9 times e to the minus 2t. So this is y2. So I have now the general solution will be c1 times y1, which is e to the t, plus c2 y2, which is negative t over 3 minus 1 over 9 e to the minus 2t. And here's the general solution. Also notice that one can factor out 1 over 3 with the constant c2. So if you factor out, you can write this as c1 e to the t minus c2 over 3. Yes, I will take minus as a factor also, so I have 3t or t minus 1/3, or you can plus, sorry, 1/3, so you can factor out 1 over 9 if you wish, it's fine. So now here I'm gonna call all of this by new constant. I will keep call this c2, so it is c2 here, and I will keep call it c2, so I can find the general solution of the form plus c2 times t plus 1/3 e to the minus 2t. So you can factor out any constant from y1 or y2. So here's the final answer, and I wish you be able to go through all the exercises in the book after you watching this lecture. See you next lecture.